Okay. I think we can start. This is our last appointment for what regards the lectures. And as you know, it's the subject of this last lecture is, I'm turning the phone off, just give me a second, because for some reason it refuses, okay, now it's okay. The subject is climate change, is a discussion on climate change, with a particular focus on the water cycle, because climate change is a very, you know, it's a very large topic. It's multifaceted because it's a topic that can be studied by focusing on engineering, on economics, policy making, politics, political science, and because it's an issue, it's a global challenge, it's a global issue, and therefore as such it involves the whole global community, the whole human community at large. We will focus, of course, on engineering, but we will be even more specific because we focus on climate change, on water cycle. We will have also a focus on the ocean system, oceans and seas system, because it's part, the oceans and the seas play a relevant role within the water cycle, but our focus today will not be specific on oceans and seas, but will be on the water cycle at large. I already made an introduction to the topic. I explained why it's relevant to engineering and why it's controversial. So basically the fact that it's relevant to engineering because it's related to policy making and to global strategies, and the fact that it's indeed a global challenge make it a relevant issue. I'm not sure if I already mentioned to you that there are two main strategies that we can adopt, two categories of strategies that we can adopt in order to fight climate change. And these two categories are mitigation and adaptation. So mitigation means a reduction of the emissions. It's a global endeavor, it's a global effort. It's characterized by long time scales because the Earth system is characterized by relevant inertia, and therefore the effect of mitigation is expected to be seen in the long term. Adaptation means that we try to understand how climate is evolving, we try to predict what the future climate will be, and then we try to minimize, to mitigate the related risks, the related adverse consequences with protection measures, with measures that may be structural or non-structural, like insurances, for instance. In a way, we don't specifically aim to mitigate climate change, this is mitigation, but we try to adapt to it. This is a category of strategies that is more local, and therefore it's involving the responsibility of local administrations. It's also effective in shorter time scales. You understand that if you build a seawall to protect the land from sea storms, the effectiveness is in the short term. The effect can be seen already in the short term. And therefore, adaptation and mitigations are strategies that can be ideally integrated. Unfortunately, the controversy of the debate is also related to the priority that we should give to mitigation rather than adaptation, or vice versa, because, of course, our resources are limited, and therefore there is a group of scientists who are convinced that we should give strong priority to mitigation, dedicating a large part of our resources to mitigation, because they are convinced, rightly, that mitigation solves the problem at its roots, solves the problem completely. While there is the feeling that adaptation may be a temporary solution. On the other hand, there are other scientists that are more convinced that a proper weight should also be given to adaptation, precisely because the time scales are different. We need immediate solutions to some problems. And also there is the feeling that even if climate change was eliminated, some problems that are originated by climate variability, which is more or less may be independent on climate change, these problems may not be solved even if climate change disappeared. Keep in mind that our society is strongly evolving, so some problems that were not considered to be so urgent in the past now are becoming more urgent. And for instance, while in the past you may tolerate sea storms once in a while because, the impact was more limited, because even if the flooded area was the same, the value of the affected land was lower in the past. And also the use of the land was less intensive. Now, if you get the same area that is flooded, you get a more consistent damage because there is a more intensive use of the land and there is an higher value of the affected areas. And therefore, there is the convincement by some scientists that even if we resolve the problem of climate change, even in this case, climate variability would continue to cause risks and damages. And therefore, this is why they insist so that some priority is also given to adaptation. This is an interesting discussion, and of course the answer also depends on the local context. It's clear that there are contexts that are more exposed to climate change, there are contexts that are more exposed to climate variability, and therefore the local conditions play a relevant role. Moreover, there is to say, I think that I already mentioned this to you, that we realized that the same change in climate causes different levels of risk depending on the local context, and in particular depending on the societal organization, depending on how the water cycle is evolving. So an increase of an extreme rainfall or an increase of an extreme wind may not be a relevant concern if the land is less exposed or well protected against climate change, against extreme sea storms. When you get instead situations where there are critical conditions also from the point of view of the societal organization, critical conditions from the point of view of the water cycle as a whole, and then climate change may be a reason of greater concern, and therefore, depending on the local situation, depending on the risk amplification, after climate change, you may get an amplification of risk, of climate change induced risk due to local conditions, as I said. Depending on these conditions, the priorities that are to be given to mitigation and adaptation, of course, change. I think that a good way of getting informed on climate change and what are the priorities that we should allocate to different solutions, the best way is, first of all, to try to get information on the science of climate change, evidences and predictions of the future. We know that an hard fact of climate change is the increase of temperature. I mentioned to you that this is a graph that is a bit controversial because it's a bit conservative. It takes the worst reconstructions in terms of global warming, which in a way I think it is an interesting figure because clarifies what is, even in this conservative, within this conservative approach, what is the magnitude of the global warming, and this is average. So the magnitude, as I mentioned last time, is about plus 1.2 degrees with respect to the pre-industrial period, with some, you see, some variability during this period, which it's, as I said, a global average. There are hotspots, as I mentioned to you, like in the Alps. In the mountain areas in general, we observe increased warmings. So this is an hard fact, and we start from this. This is what is called global warming, and of course it induces effects that are melting of glaciers and ice caps, and then sea level rise. It may induce an increase of a change in precipitation dynamics because when it is expected that under warming we get higher evaporation from the Earth system, and we get a higher capacity by the atmosphere to store water according to the Clausius-Clapeyron equation. And therefore, changes in precipitation are expected, which imply changes in river flow distribution and also river flow regime, changes in seasonality. And many of these changes are not completely understood. And this is why I think it is important to make an effort to try what the data tell us. And this is the spirit that is adopted here in this lecture, where there is, first of all, a focus on the natural variability of climate. We get here into definitely controversial topic because natural variability is what could cause a climate change in the short term, which is not related to the human influence. And why it is controversial in particular? Because you understand that if we admit that at least part of the observed changes are due to natural variability, this means that the solution is not the reduction of the CO2 emissions to prevent natural variability. Because natural means that this variability is caused by a natural process and not by human emissions. You may say that this is counterintuitive because what we observe is an increase at the same time of global warming. We observe an increase of the concentration of CO2 in the atmosphere. And therefore, one may say it's clear that temperature, there is an increase of temperature which is caused by an increase of CO2 emissions, which in turn have been caused by the human activities. Actually, what is observed is that, and we will see some figures, that even in the past, when humans were not there, there was always a high correlation between CO2 concentration and temperature of the Earth. In the past, we had changes in temperature that were an order of magnitude, as we will see, higher with respect to the changes that we have observed during global warming. But these changes are supposed to have taken place during longer periods, but still we observe during these changes of temperature that always there has been a higher concentration of CO2. You may wonder how we measure a concentration of CO2 in the past. We can measure it through ice prospections, ice carrots that are taken in the ice cap, and then by measuring the isotope composition of these ice carrots, we can we can reconstruct the concentration of CO2 in the past. So what is the reason why, even in the absence of human, there is this strong correlation between CO2 and temperature? The reason is that by increasing the temperature, then you get an increase of the temperature of the oceans as well, and then they release CO2, because the oceans are a very large CO2 storage, which is released if you increase the temperature of the ocean. I'm talking of something that is really highly controversial, because the nature of this correlation is not well clear. We are talking about reconstructed data of both temperature and CO2, and therefore this mechanism has not been completely understood. But this is one of the reasons that brings some scientists to advanced doubts on the real effectiveness of the CO2 emissions by humans with respect to the CO2 emissions by oceans. Of course, the question is whether it's warming that triggers higher CO2 concentration, or the other way around, higher CO2 concentration that trigger the warming. In any case, what is concerning is this kind of feedback, because of course, and this is the argument that is brought forward by the scientists who are very concerned by the influence of human emission. They say that there are naturally feedbacks that tend to relate CO2 emissions, CO2 concentration with temperature, and if we perturb this delicate equilibrium, of course, the human influence may be the reason, the driver that triggers a disequilibrium situation that is self-reinforced by the feedbacks. It's reinforced by the feedback. So the question is indeed relevant, and therefore this is why the topic is controversial, because of course also the solutions are different. And I think that a first look should be given to the glacial period. And here you see a reconstruction. It's a public domain figure. It's a reconstruction of past glaciation. Here, the time scale is millions of years ago. So we start from 0 on the right, and we go back to about 5.
I can't skip because of the view, but
it's not strange. Yeah, I understand. Because it's still, I think it is turned on, but indeed, let me check. Maybe that there is no connection with the projector, because it's turned on, but let's go.
Can you have the slides here, please?
Yeah, but in any case, I think it's not a big, shouldn't be a big issue to check. You have the slides you too, correct?
Yeah.
Mm-hmm. Oh, now it is coming. Okay, very good. So we go back here to about 500 millions of years ago, and what you see in the vertical axis, it's the concentration of an isotope which is used to reconstruct the past temperature, and basically what we see with the blue line is a short-term average, it's a moving average, and the black line is a long-term average. And the gray band is the uncertainty range, and this is basically describing long-term evolution of oxygen isotope ratios. This is this O18, and it is taken from fossils analysis, and it was updated in 2004, and it doesn't indicate the progress of temperature, but it is giving the position in time of the max and min. So what can we see from this graph, which is interesting? What can be seen, what we can see here is that now we are in a cold period. Now, actually, we are in the tail of a glaciation. The last glaciation, which ended about 10 millions of years ago, it started about, you see, 60, 70 millions of years ago. It's now ending. So we are in the tail of this glaciation. And if you look at the past, there were periods like 100 million years ago where the temperature of Earth was much higher, and the global temperature has been estimated in something like between 5 and 10 degrees higher. And also you see that there are these oscillations whose drivers are not known. There are hypothesis assumptions. For instance, the peaks may be given by increased solar activities, and also the low temperature period may be caused by decreased solar activity. But there is also a relevant role that might have been played by volcanic eruptions, which last for a long time. So maybe that the current cold period is given by a volcanic eruption that occurred something like 90 millions of years ago, 90, 100 millions of years ago. Another motivation could be the impact of meteorites, which may have changed the inclination of the terrestrial axis. And you know, in the presence of an atmosphere and in the presence of a water cycle that models, shapes continuously the Earth crust, the possible impact of meteorites may be something that we don't know because the traces have been lost. When we look at other planets like Mars, we see the presence of a continuous distribution of craters because Mars doesn't have an atmosphere, and therefore there is the traces of the impacts remain for a long time. And in fact, there is one of the hypotheses that we formulate to try to explain the fact that water disappeared from Mars is precisely the possible impact of meteors. And you know that it's already accepted that on Mars there was a lot of water, and on Mars then there was an atmosphere. Now there is no water anymore, and the atmosphere, there is no atmosphere anymore. So the reason maybe some people postulate that the reason may be the fact that the nucleus of Mars decreased its temperature. This is normal. I mean, also the temperature of the nucleus of Earth is continuously decreasing. And when there is a decrease of the temperature of the nucleus, there is also a decrease of the intensity of the flow of the internal streams of magmas, which bring with them metals. And the circulation of these magmas and metals is one of the engines that build the magnetic field of the Earth. So one of the hypotheses is that with the slowing down of the internal circulation, Mars lost its magnetic field, and in the absence of the magnetic field, the atmosphere becomes unstable. Unstable because there is a decrease of the power of the screen that protects the atmosphere from the solar radiation. So this is an hypothesis, but another hypothesis is that maybe that the impact with a meteorite may have caused a change in the inclination, a change in the equilibrium of Mars, which caused the disappear of the atmosphere, and without atmosphere also the water cycle gets stopped, and also there might be the degradation of water to hydrogen and oxygen for the effect of the strong solar radiation, which is not protected, which is not screened by the magnetic field anymore. So, I mean, there are several possible explanations for these ice ages. We know that there have been many of them, and here there is a translation in terms of temperature. So here you see that the scale is more or less the same in this figure, and the temperature variation with respect to, I think it is with respect to the current average, yes, because you see that in the last part of the graph is around 0. So this is delta with respect to the current average, and you see that the oscillation of in terms of degrees centigrade is from -8 to about +4. This is what gives to you the order of magnitude. And look at the concentration of carbon dioxide in the middle graph, which highlights that indeed there is a strong correlation. When you see the max of temperature, you have the max of concentration of the carbon dioxide and vice versa. And then you see also the last graph, which is probably the less interesting for us, which is the dust concentration. This graph shows that there is a tendency of dust concentration to increase when the temperature goes down. From this graph, basically, you see that indeed these changes during the glaciations have been very significant. And the question is whether, as I said, whether there are physical explanations besides the assumptions that have been made. Keep in mind that there are some causes for the change of temperature that are well known. For instance, like the Milankovic cycles, we will see a focus now. And there are other causes that may have induced these changes, like the movement of tectonic phases, and also the orbital dynamics of the Earth's system, meteorites, volcanism. And there is a review here. Let me see if the link is changing. Yeah, there is a review of possible causes here, and astronomical cycles, atmospheric composition, rise of mountains, plate tectonics, and ocean currents. Let me see. This is I'm looking at. This is the figure that I took. Here is a little bit larger. Oh, I made a mistake. Sorry for that. I think, let me check. I made a mistake with the time scale. In fact, I was not getting oriented when I was commenting the figure. These are thousands of years ago, not millions. So this figure is millions of years ago, and this figure is thousands of years ago. So this is 500,000. So this change here is a change that is related only to the past 500,000 of years. So you cannot compare with this, because 500,000 is it is focusing only on the very final part of this graph. And then you understand what happened in let me call it the recent past, okay? And you see that indeed there are, even in the shorter time scale, there are relevant changes. If you look at the shorter time scale, it looks like we are in a warmer period now, okay? And here now we have a focus, but let me go back here. And now let's have a look, because they are interesting, at the Milankovic cycles. What are the Milankovic cycles? And basically, the Milankovic cycles describe the collective effect of changes in the Earth movement on its climate over thousands of years. And he hypothesized, Milankovic, in 1920, that variation in eccentricity, axial tilt, and precession combined to result in cyclical variation in the intra-annual and latitudinal distribution of the solar radiation strongly influenced the Earth climatic patterns. And this is something that is accepted in the climate literature, but cannot explain the recent global warming. So what has been discovered by Milankovic, we don't go into the details, but here, if you're interested, there is explained what is the eccentricity, the axial tilt, we know what is, and the precession, which is a change, it's a periodic component. So the Milankovic cycles are cycles, so they have a periodic component. But the periodicity of the Milankovic cycles doesn't coincide with the global warming period, doesn't explain the recent global warming. Okay, but now let's focus, let's zoom on the most recent period of temperature. Here the scale is from the year 0, so it's about 2 orders of magnitude. This is 2,000 years against 400,000, the second graph. And what we can see here from several different reconstructions is that even in the short term, we can recognize significant changes. And in particular, from this graph, you see that there has been a relatively favorable, I would say, relatively cold period in the first part from the year 0, let's say 0800, and then there was a rise of temperature up to 1200, more or less, and then there was a significant decrease of temperature from about 1300 to 1700. And then a warming period started, as I mentioned last time, around the end of 1700, of the 17th century. And this warming period is still continuing now, with steeper increase of temperature in the past 30 years, which is the global warming. So, first of all, this reconstruction has been documented by also several witnesses that were recollected by historians. So this is a reconstruction that has mainly been based on witnesses which have been collected mainly in Europe, because, you know, Europe was civilized already at that time with civilizations that were well developed and left memories. So a first question is whether this progress of temperature, which was reconstructed for Europe, is representative of what happened everywhere. So this is something that we cannot say it's a global reconstruction. But if we look at this reconstruction, we can recognize, for instance, what has been reported, that one of the causes of the collapse of the Roman Empire, some historians say that one of the causes was a change in climate, which caused disastrous consequences in terms of floods, drought, etc. We should keep in mind that if we look at the past, the warm periods were characterized by opportunities, by more healthier conditions, while the cold periods have been characterized by disasters. This is widely recognized, and in fact, we acknowledge today that global warming may bring some opportunities. Of course, the challenge is to avoid the negative consequences. But what I wanted to point out is that there is in some opinions, there are some opinions that attribute one of the causes of the collapse of the Roman Empire precisely to some decrease of temperature, which you may recognize from this graph. I would say in all the reconstructions, different colors means different reconstructions. It's not a big change, but if you look from 400 to 600, 700, you see that there has been some decrease of temperature. And then we know that the relatively healthy conditions and prosperity that came in the Middle Age was due to an increase, let's say, improved climatic conditions. If you look at Europe, around the year 2000, it was a period of crisis, and probably around that year we started to improve the climatic conditions. If the climatic condition improve, if you think of an economy that is mainly based on agriculture, you understand why prosperity is directly related to good climatic conditions. And indeed, in the medieval warm period around 1300 up to 1400, in Europe, civilization were flourishing. And we know, for instance, that here, in this region, the Casata d'Este made a lot of investments in order to promote agricultural cultivation and to promote the reclamation of lands. So previous marshes, lands that were covered by marshes, were drained by enormous investments in order to further promote agricultural cultivation. And we know that the Casata d'Este was in trouble when, after 1500, a series of floods occurred. If you look at the flood marks of the Po River and the Tevere River, the historical rivers in Europe, you recognize that from 1500 to 1700 there were a lot of floods. And this caused the collapse of this societal organization who invested a lot instead in land reclamation. You understand that land reclamation, if you have a sequence of floods, it's seriously compromised. And then we had, after this, what is called medieval warm period, there is also a Wikipedia page if you're interested. We had what is called the Little Ice Age, when I mentioned there was an expansion of glaciers. There was an expansion of glaciers also in the Apennines, and in the Apennines, the people were used to see that the mountains were covered, the highest mountains covered by snow during the whole year. And this is also a possible explanation for some myths in the Alps who talked in this period, which was a very cold period. In the Alps, there were myths and legends who talked about lost valleys, lost prosperous valleys, which some people tried to discover because they got some memories from the far past that in the mountains somewhere there were some very prosperous valleys, and there were expeditions of people to try to discover them. And we now attribute these myths, these remains, these memories to this change of temperature. It is possible that in 1500 they could cultivate valleys that were subsequently covered by glaciers for the whole year. And indeed, if you look at the glacier retreat that we had after the post-industrial period, with only 1 degree of temperature raise, basically you can indeed recognize that probably during a long warm period they had a big change in the environmental condition that then was reverted by the new glaciation. So you see that to understand this variability, and this variability, it's natural. I mean, there is uncertainty here in the reconstructions, but you can recognize a common pattern. You can recognize that indeed there has been changes that were really significant. Here we are talking about more or less plus half degree, and the decrease is from minus 0.8 to 0 more or less. So it's indeed natural variability may play a relevant role, and we don't have for this short time scale, we cannot explain this with the effect of volcanic eruptions, because we don't have memories in the past 500 years of volcanic eruptions that were so effective in bringing a change in climate. So what could be the reason? Maybe a change in solar activity, maybe something that we still don't understand. And so the question is whether global warming now could be at least in part due to natural variability. What we can see is that if you look at the slope of the warming, so first of all, we should just, for now, not look at this black line, because this is a prediction. It's not based on observations. So if you look at these reconstructions at their end, you see that the spread between the reconstruction is lower in the recent past because data are less uncertain. The spread becomes much reduced from the beginning of the observational period. Observations are widely available from 1850, and you see that there is not much spread. And then the black line is a prediction. And this graph goes back to about 2000, and it was issued about 20 years ago. So basically, in any case, if you look at the prediction, you see that the pace, the increasing trend, the gradient of the increase is much larger in the recent period. So this is an argument that is mentioned in order to support the idea that indeed the human emissions may have played a relevant role here. But still the question remains, I mean, as I said, the question is not whether humans are effective on climate. The answer is definitely yes, but the question is whether there is a partial contribution of natural variability. So now the question is, what could be then a way to make a prediction? So what if we want to try to predict the climate and then weather in 2050, 2100, what is the best way of making a prediction? And we will discuss about this. So let's now look at, let's now talk of rainfall. So, okay, this is
the longest rainfall recorded in Padua.
Yeah, yes, and let me see, I'm not sure if I have here, I have a graph, I think, let me see. It's a paper that was published by a colleague, let's see, where, okay. There is a graph that I'm showing to you, but when we talk about rainfall, Padua is the oldest rainfall series in the world, in daily rainfall. It's amazing, and this is really a treasure. I'm not sure if I already mentioned to you, in Italy we are lucky because we have a wealth of data related to rainfall. We have some daily rainfall series that go back to the, I would say the oldest is Padua, which started in 1725, so it's 18th century, but in the 19th century, in 1813, observation started in Bologna, Firenze, and Genoa. And so we have about 5-6 daily rainfall series in Italy, which are more than 200 years long. And this is a treasure. It's a treasure because it is the only country. I mean, these are the oldest rainfall series in the world. I have a graph here, and this is Padua. You know, this rainfall series, there is the problem of data reliability for very old observations. So you see that here, they have identified the names of the location of the rain gauge because it was moved. When you move a rain gauge, it's potentially a problem because there might be some inconsistency in the measurements. But also if you build buildings around the rain gauge, there might be some influence because the rain that is measured by a rain gauge depends on the environmental condition. The presence of wind, for instance, has a strong effect on the measurement. So basically they tried to check also if the reliability of data can be considered homogeneous, and in part this series was corrected. But if you see here, there are the modern instruments. The modern instruments, they assume that give observations that are less affected by uncertainty, of course. But actually, if you take a look, just a very, very rough picture, it's hard to see changes immediately. You understand that while with temperature, let's go back here. You look at this, you see changes, it's clear. And with rainfall, it becomes more complicated. Why? Because rainfall is intermittent, first of all. Temperature, it's not very much varying. It's, it's very slowly varying. The variability, it's not very large. If you look at rainfall data, today you may have the sun and tomorrow you may have a storm. With temperature, it's unlikely that you have these big changes. With rainfall, it's normal. So while here the situation is quite clear, here you have to, you have to have a refined look. Of course, you can see some periods where rainfall was lower. Keep in mind that when we talk about climate change, we are concerned by both extremes. If we have low rainfall, we are concerned. If we have too much rain, we are concerned, of course. So this is the graph, but here you can see zoom and a moving average. And here, these are actual, it's the annual rainfall total here with a moving average. And here it's annual number of wet days. This is another variable which is interesting because when you have large number of wet days with the same amount of rainfall, it means that the intensity was lower. So if you have the same amount of annual rainfall, but it rained every day, you understand that the amount of rainfall every day was very low, so the intensity was low. When you have a decrease of rainy days, with the same annual rainfall, they imply a decrease of rainy days implies a higher risk of flood because it means that all the rainfall is concentrated in few days. The opposite situation brings may bring other consequences. I was saying it means an increase of the drought risk. Actually, I would say that in general, on average, when you have the rainfall that is concentrated in few days, you have an increase of both risks, drought and flood. Flood for obvious reasons, because of the higher intensity. Drought because groundwater is not recharged if you have a lot of rainfall concentrated in few days. But these are very interesting graphs. And this is looking at the extremes. And if you look at the extremes, it looks like there is indeed an increase of extremes in the last period, but this started well before the global warming. So it is hard to attribute it directly to global warming. So the analysis of rainfall is a bit tricky. And first, let me say that it is known that environmental variables may be affected by cycles, which we cannot easily explain. We have seen Padua series and also temperature in this case. These cycles, unexplained cycles, were discovered by an hydrologist, who was Harold Edwin Hurst. I'm looking for a picture, but I don't have here any picture. How this hydrologist discovered these cycles. He was, let me see here, but I think this is a paper, so it's, yeah, this is a paper, let's forget about it. How Hurst discovered the presence of cycle? Very simply, he was called to design a sequence of dams along the Nile River around 100 years ago. He had this great opportunity to make the hydrologic design. He was in charge of designing the optimal size of the reservoir. What is the scope of a reservoir? The scope of a reservoir is to store water during the wet season, to distribute it in the dry season. And you understand that the largest difference in rainfall between the wet season and the dry season, the largest the difference, the larger the reservoir. If you had constant rainfall, you wouldn't need any reservoir. If you had constant river flow, if the Nile River was just constant, no reservoir is needed. If you have indeed a change, a big change between the dry and the wet season, then you need a larger reservoir. So what Hurst did is to study the differences in river flow. Sometimes I use river flow as a synonym of rainfall. I think you understand the difference. He was looking at the differences in river flow in the Nile River between winter and summer, their winter and their summer. The Nile River has only one maxima in the regime. It's not like our rivers that we have two maxima, spring and fall. The Nile River is only one maxima, so it was quite easy for him. There is only one dry season, only one wet season. He looked at the difference. And what you would expect is that every year, more or less, you have the same result, more or less. Of course, you have differences from one year to another, but what you expect is that if you look at the first year, you get a value. The second year, the value may be a bit different, but when you increase the number of years, he was expecting to see the same optimal size for the reservoir, because, you know, the difference between high and low flows, it is expected to be statistically more or less the same. Actually, what he found is that the longer the period, and he could analyze a very old record by the Egyptians, they collected very long records of the Nile River flow. He went on and he realized that when he increased the size, the number of years, the reservoir was keeping increasing in size. And he didn't understand why. The reason is that there is not only the annual cycle with the max and the mean, but there was also a long-term cycle superimposed. And therefore, as long as he went on with the years, the reservoir size kept increasing. And this is what he termed, he didn't term it, other terms the Hurst effect, which means that you have very long cycles. And this is something, as I said, that it's not yet explained why the Nile River should be subjected to these long-term cycles, like 10 years of low flows or 10 years of high flows. By the way, if you look at the Bible, we know that in the Bible there is written that in the past they experienced 7 years of famine followed by 7 years of abundance. And this may be a reflection of the presence of these cycles. So this is something that we know, but we still can't explain, which complicates our assessment of human-induced climate change. And you may wonder why these evidences of natural variability are frequently not mentioned. The reason is that when we talk about climate change, we want to be very conservative, very precautionary. So it's clear that if we assume that there are several uncertainties, then, as climate scientists say, then of course our conclusions regarding climate change, our call for action would be less effective, would be less effective in terms of convincing politicians to take actions that are not very popular. And therefore, they prefer to rely on what is known and assume that these changes in the past 30 years are due to indeed increased CO2 emissions. You may think that this is not really a precautionary approach because I mean, when you dedicate resources to solving a problem, also a precautionary approach would suggest that you propose a solution when you are fairly confident on the effectiveness of this solution. But keep in mind that here we are talking about a global challenge. We are talking of something that may need an urgent intervention, and therefore unknowns are often neglected for the sake of being sure to take the most conservative approach. And this may explain why I think it's the first time that you hear talking about long-term cycles. Probably it's the first time that you hear about the medieval warm period, the little ice age. The reason is that, you know, it's clear that in the current debate, if we introduce a lot of uncertainty in the scientific conclusions, then the scientific conclusions themselves may be less effective in indicating a way forward. And you also understand why the topic is controversial. And, you know, I recently assisted to a debate where a graph like this was published by a scientist, a very known scientist, a French one, who said, look at the correlation between carbon dioxide and temperature. He was looking at that and basically simply concluded, very simply, because I mean, it's a trivial conclusion, that we cannot say anything about what effect started first. Was the temperature starting first or the carbon dioxide starting first? And basically the paper that he published was subjected to a re-review and then was withdrawn because the re-review suggested that the paper was not accurate. Actually, I looked at the paper, I think it was not so accurate, but I was also amazed by the strong reaction because there are a lot of papers that are not very accurate, but they are still published and they stay there. So this was withdrawn and it's still accessible because when you publish something, there is legislation that forces to keep everything is published available, but there is an inscription saying the paper is not reliable and therefore I'm missing the English term to say that because it was not withdrawn actually, was, okay, I will remember. Anyway, I think the concept is clear. Now, let's look at river flows. This is a figure I'm proud of because I built it, but it's actually, it needs some interpretation. So this is a picture in 3D of the Po River flows. The time series of the daily flows of the Po River at the closure, Ponte Lagoscuro, which is quite close to here. It's a long time series. We have continuous river flow measurement from January 1st, 1920. There were also past measurements, but not continuous. But from January 1st, 1920, we have continuous measurements. So the time series is already more than 100 years long, which means 36,000 of observations. And I was stimulated to look at the distribution of the river flows. And therefore, I thought that I could draw a graph. And let me see if I could block it, because the problem of this image is that, let me see if I have a fixed one, no, But let me do one thing. Because it's nice that it's rotating, but if you have to read it, it's not very convenient. So in the paper, it's in the paper, the figure there are both the moving figure and the fixed one. So let me just get it. Okay, here it is. Okay, so I thought that it may be an idea to put the years in one horizontal axis. So you see from 1920 to 2000, this was from 1920 to 2009. And the day of the year on another horizontal axis from 0 to 365, and then the river flow in the vertical axis. But the river flow is smoothed. Smoothed means that because otherwise it wouldn't be possible to read the figure. So I smoothed the surface with a filter, a moving average. And what you see here is something that is very, on the one end is very trivial. There is the dry period in summer, around the days July. There is the July-August dry period. There is the dry period in winter, which is less pronounced than the dry period in July. And there are the two high flows periods, the spring one and the fall one, the autumn one. And in general, in the Po River, the highest floods occur in autumn, October, November. But you see that on average, the flow is higher in spring. So if you look at the river flow volume, the higher values of volume are in spring, if you look at the seasonal volume. If you look at the peaks, you have the highest values in the fall season. But what's interesting to see here is that first, the cycles. If you look at the summer drought, you recognize that there are periods, drought periods, and relatively abundant periods. Here you can recognize that there was a drought period at the beginning, and then from 1930 to 1940, the summer flows were fine. There was a big drought, which is well known, from 1940 to 1950, 55, and then an okay period. And then there was another drought period after 2000. You may remember, you probably were too young, but in 2003 and 2007, we had two extreme droughts in the north of Italy. Okay, let's look at the floods, and what we can see is that there are clusters. So here you can see the flood of 1951, and then the flood of 1970, and the two big floods, the two larger actually, in 94 and 2000. And then here there is another quite significant flood. It was in June. I don't remember really the year, but it was between 65 and 75. But what's interesting here is that you see a pattern. For instance, one curious thing is that isolated peak of high flows at the beginning of the spring, which is present only here. So from 1940 to 1970. And this may be due to snowmelt from the Apennines. This big one is snowmelt from the Alpine region. But this one may be snowmelt from the Apennines, and which disappeared during global warming, which is possible. It's possible that we got less snow in the Apennines during global warming, and the related flow was shifted. And I think this figure is interesting because it allows to see that indeed there are cycles. Just a second. I think, okay. Let me see. Okay, this is the original figure rotating. By the way, this figure was done by R, quite easy to do. it's not complicated. Even if the code that I prepared, which was made available public domain, it doesn't work anymore, because I tried to reproduce the figure just 1 month ago, and I had to change some of the instructions because some functions became obsolete, and it's still possible, but the code that was made available to make this figure doesn't work anymore, which is still available from my website. So basically, what is the conclusion? The conclusion is that we have cycles. These cycles are evident in temperature because temperature has less variability with respect to rainfall and river flow. Rainfall is between these three variables. It's the one with the highest variability, but still we can see cycles in rainfalls, and we can see cycles in river flow. River flow is a filtered version of rainfall, and you see that indeed even here there are evidences of climate variability, which natural variability, which are very relevant. But one thing I want to say before I move forward, and before talking about more explicitly about the human influence. I mean, if you think in terms of adaptation, it doesn't change much whether we adapt to a climate change or climate variability. More or less, you can find a common root in the strategies to adapt to climate variability and adapt to climate change. And the presence of this common root allows us to devise no-regret solutions and suggest a possible way to adapt to climate change. And the possible way is to look at the current problems, to look at the current challenges. So we have this natural variability on the Po River, which is a matter of concern because we see that there are droughts that are very concerning. Even in the period pre-global warming, there are floods that are very concerning, and we are not protected against these disasters. And therefore, I think that no matter if it's human influence or natural variability, we have something to do, and this gives a suggestion for a clear way forward. It's fine to rely on climate predictions, but if we have uncertainty, let's focus on what is less uncertain and still presenting a challenge. So in terms of sea level rise, what is the challenge? The challenge is the fact that already now we have seawater intrusion. I'm not sure whether you attended, probably not, my lectures in the fall on saltwater intrusion, but this is a relevant problem here. We have saltwater intrusion, which is really exacerbated even by a small change in average sea level. So even if you add 10 centimeters to average sea level, saltwater intrusion would progress a lot. And therefore, saltwater intrusion is already representing a challenge. Let's focus on what is already a challenge, and let's solve the current problems. This is for sure a no-regret solution. And then keep in mind that if it's not purely natural variability, but there is also some human component in the change, then it means that we need a flexible solution. So the solution that we design can be adapted in the future if variability increases, if other changes come. And this is a question that you should consider, because if there is the possibility that the no-regret solution is made flexible without, dedicating a significant amount of additional resources, this is a way to follow. And if additional resources are required, then we need a proper evaluation. But what is, suggesting the way forward, and it's already a preliminary conclusion of this discussion that I want to undertake today. A preliminary conclusion is, let's focus on the current problems, and whenever it's possible, let's adopt a flexible solution. Now, let me make a more refined discussion about the human influence, but I don't want to spend much time on this. The human influence, as I said, it's unquestionable, unquestioned. There is for sure a human influence on climate. I think I already mentioned the heat island effect to you, which is the fact that in the urban environment you have a higher temperature. And this is a relatively recent problem, because we had an expansion of cities in the past, starting in the past centuries, but this expansion is still continuing. And the urban heat island effect is increasing and increasing, which implies an increase of pollution, a decrease of the living conditions, etc. Also, it implies a water resources problem, but let's focus on global warming now. So this is a demonstration that there is a human influence. And I mentioned the Clausius-Clapeyron equation, which gives, specifies the temperature difference of pressure, and most importantly vapor pressure, because the Clausius-Clapeyron equations tells us that for any increase of temperature you have an increase of potential water storage in the atmosphere of 6–7%, between 6 and 7%, which means that our current atmosphere is able to store 6–7% more water with respect to the pre-industrial period. And this is for sure a cause of climate change. And I want to mention that human impact on climate may be assessed through deductive or inductive approaches. What is the difference? Deductive uses models, and this is the mainstream today. We try to predict the future climate by using models. Climate models where we put humans into the system and try to understand what is our best prediction for the future climate. The inductive approach is using data. It's looking at past changes and tries to extrapolate these changes into the future. Just be aware that there is another controversy regarding these two approaches, because typical engineers are convinced that the data are more reliable than models. Scientists, researchers have the opposite convincement, that models are more reliable than data, because data are subjected to measurement errors. But indeed, now the mainstream, which is, I think, well justified, is to apply climate models for estimating the future climate. What is a climate model? A climate model is a digital twin. This is a term that became very fashionable in the recent past. A digital twin of the climate system, which means that we try to reproduce mathematically the processes governing the evolution of climate. These processes are highly heterogeneous and are typically described through conservation equations, which means that, given that they are highly heterogeneous and expressed in the form of conservation equations, they are governed by equations in differential forms, which is not a problem. I mean, we have now powerful computing capabilities to perform numerical integration. But one important thing to know is that in view of the heterogeneity of the processes, these equations are applied at the very local level. So the climate system is represented through a three-dimensional grid. And the equations are applied at each grid cell, which means that then you move to the next one, and depending on the computation that you previously performed on the neighboring cells, you perform the computation of each cell in turn. I mean, the computational requirements is quite important, and what is important also to consider is the scale, time scale and spatial scale. So the resolution of these models now, it's of the order of 10 kilometers, which 10 kilometers is, I mean, if you consider the whole globe, it's a great resolution, it's a very fine resolution. On the other hand, if you want to describe very local processes, you understand that, for instance, for describing the convective storms, the summer convective storms, these models have a limited capability of describing them. But this is probably the future, the attempt to reproduce with the digital twin the whole Earth system. Of course, there are uncertainties like in any model, and the fact that they are applied at the very local scale make also numerical uncertainty very relevant. Okay, now let's have a look, a more refined look to recent changes in hydrometeorological variables. We already mentioned precipitation, but let's have a refined look. And here we will also have a look at the sea level. Now, precipitation, this is a nice reconstruction and of long-term mean precipitation. This is long-term mean precipitation in different months. And this is not representing changes, temporal changes. This is not representing time changes. It's representing the spatial distribution of rainfall over different seasons. And first, try to, here you don't see very well the scale, but if you look at your PC, probably you can see it. What is the order of magnitude of annual rainfall over the Earth? The average is about 1,000 millimeters, 1 meter. Just try to keep in mind this order of magnitude because it's important. So what is, in your mind, you have to have clear what is the average rainfall over the globe, 1 meter, more or less. In Italy is about, it's about 800 here, 600 in the south. We have some regions like the Friuli where we exceed the 2 meters. And here you can see the overall distribution, and where the dark blue is about 2 meters, and the green is about, I would say that it's about 500. And the white is 0. You can see that rainfall is highest at the equator, we know that, and you can see that Europe is in a quite lucky situation. It's not the most rainy region that we can find on the globe, but still we have a significant amount of rain there. Now,
sorry, 1 meter, 2 meters per month?
No, 1 meter of rainfall per year, annual rainfall.
Okay.
Annual rainfall. This is here, you know, it's not easy to see, but yeah.
So you multiply by 10.
Yeah, if you look at the legend here, you have the green in 40 per month, which means 500. And you have the blue in between 100, dark blue is between 100 and 200. 200 is 2.5 meters per year. And indeed, if you look at the Friuli region, this is millimeters per month, the legend, so I multiplied by 12 in order to get the annual. And if you look indeed at Italy, you see that most of the rain is in the northwest. It depends, of course, on the season, but in general, if you look at the overall distribution, is in the northwest. Okay, now, what is the expected effect on precipitation after global warming? What we may expect is more evaporation, which means more precipitation, because the total amount of water is unchanged over the Earth. Of course, with an increased temperature of the atmosphere, you have a slight increase in water vapor, but it's not very significant. I mean, if you have a because it's 6-7%. If you have more evaporation, you are expected to get more rainfall. The problem is that the rainfall may fall very far from where the water evaporated. So it may happen that indeed there are benefits in terms of more precipitation from global warming, which do not compensate in space the increased evaporation. But this is a reasoning in principle. In practice, what is observed by analyzing pan-evaporation data is that under global warming, evaporation did not increase. This gives rise to the so-called evaporation paradox. It is something that it has been explained by a decrease of the strength of winds, because evaporation is not only related to temperature, it's also related to solar radiation, it's related to wind. Wind velocity is much affected on evaporation, and therefore, by analyzing wind data, which are quite sparse, but still they allow some assessment, we understood that pan-evaporation is not increased. And therefore, on the other hand, recent studies have demonstrated a slight decrease. And here you see the two possible explanations. So, I mean, even if the atmosphere has a higher water storage capacity, water vapor storage capacity, this does not imply that automatically we get an increase of rainfall, which is of the order of 6-7%. Because, I mean, if evaporation is decreased, then this compensates, in a way, annihilates the effect of global warming in terms of water storage in the atmosphere. Now, there have been a lot of analysis of this kind on precipitation. Let me see if I have some graphs. Okay, the next one is related to intensity. So the demonstration is that in terms of annual rainfall, which is an indicator of long-term rainfall, we don't see big changes. Globally, there is no change. And if you look at regional situations, they are compensating each other. Indeed, there are some regions where we observed a slight decrease, but there are also regions where there was a slight increase. There is apparently no effect on the persistence of drought period. So long-term droughts, it's not proved that their frequency is affected. What about extreme rainfall? The storms, the rainfalls causing floods. You know, rainfall is heterogeneous, and we don't have enough observations to reach a conclusion about very short-term rainfall. So when we talk about daily rainfall, we have time series. I mentioned the Italian ones. When we go to hourly rainfall, we have less data. And when we talk about rain of 5 minutes, the so-called water bombs in Italy, we don't have observations. And therefore, it is very hard to prove that, to say that water bombs, the frequency of water bombs is increased under global warming. This is actually not proved. I had the opportunity to make a study. I had a student from Greece. He's really great in crunching data, crunching numbers. And what he did was to collect daily rainfall for the past 50 years all over the world, and he was able to put together several stations. You see here the coverage, okay? And he aimed to see whether the frequency and intensity of extremes increased. And what he did was very simple. He defined the extremes by fixing a threshold, and then he counted the number of events for each station above the threshold and the intensity of these events. And what he found was that in terms of intensity of extremes, this is a global distribution, he found that indeed there are some changes during the observation period, which is, as you see from here, it's about 50 years. But these changes actually are not very, I mean, we are talking of changes from -3% to +3%. So it's about a range of, in terms of number of events, +7%, let's say +10 if you want to be very conservative. But +10% means that where you have one extreme per year, then you get 1.1 extreme per year. So the number, 10% in number of events, it's not really making a big change. In terms of intensity, this is what, this is the distribution of the mean number of extremes in different zones. In the northern hemisphere, there is a larger increase with respect to the southern hemisphere. And then in terms of intensity, I think there is no graph here, okay. But what he found was that there is a slight increase of intensity of events, but this is very slight. So it's about +5% at most. And the average increase was like +1%. So +1 or +5, it's not really a big change. And indeed, there were many similar studies, and the results show pronounced spatial variability, and which means that in some cases they didn't detect any change, in other cases they detected changes. And the highest changes were found, I think, in Australia. I think it was the east of Australia, where for some regions they found a max of +20%, so 3 times Clausius-Clapeyron for each degree of global warming, which means that given the degree of global warming is about 1, it means that for some region, the very extreme changes that were found are +20%. In most of the cases, they found +6, 7, which is in agreement with what we found. And so +20 is something that becomes concerning in terms of intensity. In terms of frequency, it's not really concerning. In terms of intensity, yes, but this was found only in a very restricted region. On the other hand, this is daily rainfall. Some people say that had we had the possibility to look at hourly rainfall or 10 minutes rainfall, the increases would be higher. This is possible. This is possible. But in terms of daily rainfall, really, even if we say +6%, +6, it's not really a big change.
Well, anyway, these slight changes for our generations not going to be a big deal. But if every 70 years we have 1% or 5%, you multiply in an era and
yeah, that's true.
Anyway, very interesting.
That's true, indeed, that's true. And also there is one thing to say, that we are not talking about seasonality. And seasonality has been affected as well. So this is something that is relevant for water resources management, because if you have the same rainfall with the same intensity, everything is fine, but it is shifted in time. So instead of having rainfall in April, you have rainfall in February, and you don't have any snow in February. And I mean, then the situation in terms of water resources availability may change. So here, we are just looking at the extremes in order to try to assess the risk of flood. But there are several other features that may be relevant, and we don't have enough information to inspect them. So I'm not saying that the conclusion is we are fine. No, absolutely. The conclusion is that probably we should couple the data analysis with some modeling experiments. I think we can make a break now, and then we will talk about sea level during the next couple of hours. Okay, so sea level, which is more interesting for us. First, I would like to draw your attention on a link. If you're interested in this topic, I would like to draw your attention on this link on my website, the first one that you find under sea level. Let's see if, yeah, it is still available, still working. This is really an interesting study, and I took inspiration from this study for drafting this lecture. And so just by looking at the essence of it, let me just focus on this picture, which look at the time scale thousands of years ago, and look at the vertical axis, sea level change. So the current situation is what you see on the right, with several measurements taken in different parts of the globe, because when we talk about sea level rise, we implicitly tend to assume that the sea level is the same everywhere. Actually, there is some variability. And therefore, when we talk about sea level rise, we should include also the specification that it's mean sea level rise. For instance, you know that the level in the Mediterranean is responding more slowly with respect to changes into the ocean, for the obvious reason that the Mediterranean is connected to the oceans through Gibraltar, which is a very narrow connection. But if you look at this figure, you see that the change in sea level is amazing in the time span of the last 20,000 of years. And this is the time span of the last glaciation. So we are exiting, as I said, from the last glaciation now. And the increase in sea level from 20,000 years ago has been more than 100 meters. And it is something that we know, because we know that there has been changes in sea level that are very relevant. And what is the fact? What is the reason of this change? It's indeed the glaciations. So when you store water in the form of ice, in the ice caps and the mountains, this implies a decrease of the sea level. And so, I mean, when we talk about changes in temperature, let's call them historical, but it's more than historical. It is changes in the time span of thousands of years. Changes in temperature and sea level, we are talking about something that is indeed relevant. What is interesting is to focus on the recent period, since the end of the Little Ice Age. I want to look at the link in Wikipedia for the Little Ice Age, and indeed you see this figure is relatively new. I wanted to look at this figure because it's these figures because they are frequently updated. Okay, so sorry, because I think I found a picture which is interesting. Frozen Thames, because there is a picture available, but it's not public domain, of the Venice Lagoon iced during the Little Ice Age, but I don't think it's here. There are several pictures of that kind in order to prove that indeed between 1700 and 1800 there was a very cold period, and people were skating on the Thames, and they were skating on the Venice Lagoon. Anyway, okay, so by looking at the recent period, after the Little Ice Here there is a spelling error. I didn't notice that. After the Little Ice Age, the global sea level has been steadily rising, and between 19, and this is the order of magnitude that I want to emphasize, between 1900 and 2016, sea level rose by approximately 16 to 21 centimeters, depending on the location. So this is the amount of sea level rise we are talking of from in the past 130 years. It's about 15 centimeters. And the data from satellite or radar measurements show an accelerating rise of 7 centimeters, more or less, from 1993 to 2017, which is coherent with the pace of global warming, which means that it's slightly increased, but not much really during global warming. The rise is due to thermal expansion and to melting of glaciers.
Thermal expansion, like
yeah,
it is a strong.
Yeah, it is responsible for about half of the sea level rise. Now, thermal expansion is.
I never thought about thermal expansion. Like I didn't thought that 1 degree would,
No, it's about half of the contribution.
Okay.
Yeah, because it's indeed thermal expansion is indeed important. And so I think I have a picture here. This is still a picture which is related. It's analogous to the previous one. It's related to the past 20,000 years, but I think I have a picture here. Yeah, this is from 1880. And you see there has been a slight increase in the final part of the graph, but not really that much. It looks like a steady increase due to the rising temperature in starting from the end of the Little Ice Age. And if we want to, let me see if I forgot something. I don't think so. And if we look at the very recent period, from 1990, and you see that the trend is quite steady, and therefore what one may say is that it doesn't look so concerning, because we are talking about 15 centimeters. It's really a small amount. On the other hand, there is to say a couple of considerations. First, this is global average. It's not extremes. So some people say that in terms of coastal flooding, the risk is increased more, and in terms of hurricanes, it's increased more than what these 15 centimeters may imply, which may be true, but on the other hand, again, when we talk about extremes, then the assessment of changes becomes more complicated. So it's not documented, not documented in a very quantitative way. So this is anyway the first consideration. We are talking about global average. Second, if you look at the saltwater intrusion, as I mentioned, 15 centimeters are already a significant amount, because if you think of a flat coastal area, 15 centimeters may, imply that indeed the extent of saltwater intrusion may be considerably higher. So if a reason of concern is saltwater intrusion, like it is here, 15 centimeters is something that it's to be considered anyway. And this is another consideration. And there is a third consideration, which is related to the fact that in the past we had these big changes of sea level rise. And these big changes correspond to changes in temperature that may have been of the order of magnitude of 10 degrees. So if for 10 degrees of global warming, we had 120 meters of change in sea level, what is then the progress, the expected progress, the progress that we should expect of sea level rise due to global warming if the global warming gets to 2 degrees, 3 degrees? So should we expect an exponential increase of sea level rise? And this is the subject of massive research efforts to try to understand if how the change in sea level took place in the past. And in particular, there is the concern that there might be tipping points to a certain amount of temperature, like 3 degrees of +2 with respect to now. It may happen that you have a sudden collapse of a massive portion of the ice cap, which may bring a sea level rise of a couple of meters just for a small change in the temperature, a small additional change. So a kind of amplification of risk, a kind of tipping point, which may be governed by threshold effects. And this may be explained because we recently discovered that in the deep interior of the ice cap, there are huge amounts, huge volumes of liquid water that are stored, and they are liquid because of the high pressure that in the deep interior, in a way, prevents water from icing. And then the concern is that if we start melting, then these big masses of water might be released more or less suddenly. And this may imply a sudden increase of sea level. This is the concern, but this is hard to be predicted. And this is why we are so concerned about sea level rise, because if you look at what happened so far, you may say, it's impossible that island disappears because 15 centimeters, even if you increase some more, I don't know, 40 centimeters, we cannot be concerned by the disappear of extended coastal areas because it's not much. But if the increase becomes 1 meter more, then, you know, it's a matter of concern.
Maybe you need to also consider tide, which sum up to those centimeters. Sorry if I have a question. I don't know if there is data available, but if theoretically all the ice cap melts, all of it, like the impact in meters.
There are predictions. I am not really, I don't have the numbers now. I think it is easy to find them. I would say that the prediction is about of the order of magnitude of 5-10 meters. And this is the order of magnitude. And of course, it's not only the ice cap. There are also the glaciers in many glaciated areas. And I think anyway that the order of magnitude is about 5-10 meters. And because I think the worst predictions, if you look at the IPCC predictions, I think they are here. 1 second. They are here. And if you look at the worst prediction of the IPCC, and this is the AR5 assessment report number 5. Now the number 6 has been just issued. I'm not sure if they issued also the prediction of sea level, and they have been released. The summary for policymakers has been released just 1 month ago. So it can be found on the web. I think I have it somewhere. And, but I didn't have a look, but I don't think the predictions are much different from these ones. And you see that if you look at the last period, 2100, and you look at 8.5, RCP 8.5, and the range is, the worst prediction is plus 0.2 with respect to now. And so I would say that let me see, global, okay, this is for higher prediction, so we should look at this one, 2 degrees of temperature change. mean, and then you get an extreme value of 5 already here, which I think corresponds to significant melting of the ice cap. But actually, if you, no, this is temperature change, sorry, I was looking at temperature, which is not, we should look here. The worst prediction is 0.2. And so basically 0.2 corresponds to an increase of temperature which is significant. It's 2.6, let's say more than 4 degrees. But for a complete melting of the ice cap, I have seen predictions in some papers of, I think it's about 5 meters. But this is an event that is not really, I mean, in the past we had already periods without the ice caps. It wouldn't be the first time. So we had them. And when the temperature was +6 with respect to now, I think we had periods with no ice cap. And so it may happen. And what we are trying to understand is whether when it happened, it was a sudden process or a slow one. And this is a question mark, which justifies the concern that we have for the sea level rise, because otherwise I wouldn't say, I mean, personally, I'm more concerned by the extreme rainfall than sea level rise, if I don't consider the event of a sudden increase. Keep in mind that I mean, when the changes are in the long term, it's not a problem, because if you have time to adapt, we have been adapting, humans have been adapting to changes that are very relevant. And the Earth system in general, you have seen the historic changes. So, of course, if you have time, it's not a big problem. If the changes are sudden changes, then you have, first of all, you have wars. This is unavoidable. If you think of a sudden increase of temperature of 1 degree, from the day after tomorrow, then you get wars, because you get regions in the world that were previously without any value, that would become valuable for food production, whatever, and regions that should be abandoned. So in the first instance, you have migration, but migration follows a deterioration of the living conditions. And then you have attempts to occupy regions which are richer. So when you have sudden changes of even of the economical and political setting, you get wars. This is the immediate consequence. And then adaptation, anyway, takes time. And if it takes time, it means that meanwhile we get disasters, we get people suffering. I can tell you that there are projections of models anyway that give the numbers that you were requesting, but if you look on the web, you find it. And maybe that I take some time and then I send a message in the chat. Now, about floods and droughts, I already mentioned something. I don't want, I don't want to give, to go in much details, but I want to give you some results. And first of all, the Po River. The Po River, actually, in a nutshell, we can't say much. This is the max annual river discharge of the Po River. I'm not sure if I have already shown to you this graph. It's an animated graph which shows for every year the max flow, daily flow. This is daily average. And if you fit a regression line, which is 50 years long, and move it along the time series, you see that in general you have apparently an increasing trend. Some periods it becomes decreasing when it becomes red, but on the other hand, the increase is not really so relevant. And so, I mean, if we look at the large rivers, this is a general conclusion. If you look at the large catchments in the world, in the period of global warming, apparently, it looks like there has not been a clear increase of flooding for large catchments. Keep in mind that large catchments means a catchment that is that is put in a critical situation by long-term rainfall. The Po River, when do you have floods? You have floods when you get 1 week of rain. A rain that lasts 1 day for the Po River or the Danube is not a problem. The problem is a long period, a long wet period. For small catchments, it's the opposite. Long wet period, the small catchment is not a problem. So when you get the flood on the Po River, usually you don't get flood in the small mountain rivers. It's the big one is not happening at the same time that the small ones, which is, by the way, a fortunate coincidence, fortunate correspondence. The small rivers, the small catchments are put in critical condition by short rainfall, like 1 hour, like 15 minutes. So the conclusion that applies for the large river doesn't extend to the small rivers. But for the large rivers, it seems that global warming is not causing a significant problem. So what about instead in general results for Europe? Here you see these arrows up and down, and which are flood changes that have been detected in Europe. So you see that there is some dishomogeneity, and with different colors, they have depicted different areas. And what turns out is that, in a nutshell, where floods are dominated by snow melt, an increase is found, which is something understandable, because global warming means changes in snow melt, and there are several types of floods that are dominated by snow melt. It's understandable that in this case you have a consequence. Also, I think it's explained here that seasonality is changed, and this is a paper that was published 5 years ago, which clarifies this. It's a bit slow, but it's you see changing climate shifts timing. So it is what I discussed before, changes in seasonality. And here you see later, earlier, days per decade. You see in different regions of Europe, and in Italy you see that in the mountains of the north of Italy, we have earlier floods because of snowmelt. And in the south of Italy, we have a tendency to have later floods. And indeed, there are patterns which identify also hotspots. Okay, and what about droughts? And droughts are more complicated processes with respect to floods. Their generation takes longer, they evolve in long time steps, and they are also tightly connected with the dynamics of groundwater. So what we know is that recently we have been crises in water supply systems, water irrigation system, caused by long-term droughts. But actually, these disasters have been caused by the occurrence of long-term periods, like 10 years, with minus significantly, something significant rainfall, minus 20, minus 30%, which lasted several years, but these events are not new. What is new is the coincidence of a critical situation of climate, a long-term drought, with a critical situation of the social asset, which is relying more and more on water resources. So in the past, this event happened. We have seen the Po River in between 1940 and 1950, but in the past we suffered less because of our higher resilience at that time, because we were relying less on water resources. And today, these events are a great matter of concern. But if we look at just the frequency, so at the hazard of this event, the probability of this event occurring, it's not yet clear if they are influenced by global warming. So you may notice something, a discrepancy with what the media report. The media say global warming increased the risk of drought. Actually, I mean, I think the risk is increased, but it's increased for the greater exposure. There is still no scientific evidence of increased frequency of droughts under global warming. Droughts are due to the influence of El Nino. And El Nino, what is El Nino? El Nino is a temperature difference between the Pacific and Atlantic Ocean. And when you get this shift in temperature, then you have a movement of masses in the atmosphere which may last for a full season and may last also for several years because El Nino has persistence. This phenomenon of shifting temperature between the oceans has some persistence, but actually there are still no demonstration that El Nino is influenced, El Nino and El Niña are influenced by the global warming. And there are scientists are trying to study this. Let me see, these links are the same. Yeah, the same link. And so it's here there are some more, there are a couple of links in Wikipedia. So there is no demonstration that the frequency of drought is increased, and here is the figure I was looking for. And this is an explanation of, this is La Niña phase. And so how the difference in temperature in the Pacific Ocean, in this case, can cause movement of masses into the ocean, which corresponds to movements of humidity in the atmosphere, because where, of course, where the ocean is warmer, you have more evaporation. But there is still no proved connection with global warming. But still, droughts are a matter of concern. If we focus to the local, to the current problems, actual problems, as I suggested, droughts are a problem because if you look at the annual rainfall in Bologna, this is the series of annual rainfall in Bologna, you can see, starting from 1813 up to now, you can see that indeed there have been in the past, in gray, long periods with minus 20% rainfall. And the last one was between 1940 and 1950, but it's not actually the most intensive one. There have been during the 19th century some droughts that are very concerning. If these droughts happen today, it would be really a big problem. And recently we didn't have long droughts, but still, if these events happen in the past, then it may happen again. And this is the summer rainfall in Bologna, which show a similar situation. And if you look at the minima, annual minima of the Po River, again, you see the presence of cycles. And you see the presence of periods where, indeed, the minima was very low. So even if there is no proved influence of global warming on the risk of droughts, we have to be very concerned by this risk. And keep in mind that if we associate the drought with the sea level rise, then it means, again, saltwater intrusion, because saltwater intrusion is contrasted by the flow of fresh water in the underground. It's the fresh water that is pushing back the salt water. If you decrease the flow of fresh water because of reduced rainfall or overexploitation, then you have saltwater intrusion, which is further exacerbated by the sea level rise.
And what are the consequences, the lack of good soil for farming?
Yeah, and it is, the consequence is very simple. I show you, let me take a pen and marker just one second. I think I can, instead of taking a marker, let me take a figure from here. 1 second. Okay. Let's take coastal engineering and saltwater intrusion. Let me get a figure. Okay, the consequence is this. Look at this figure here, for instance. Let me see. I think this one is the best one. Okay, this is a normal situation, and basically you have fresh water coming from the land, from rainfall infiltration, and then you have, along the coastline, you have the salt water intruding. The salt water tends to intrude because it's heavier than fresh water, so you need more fresh water in order to counteract the push from salt water. And then you have wells taking fresh water. If you have an increase of the saltwater intrusion, you get the salt into the well, and then you cannot use that water anymore. And also keep in mind that in order to recover the soil, it's not easy, because what we may try to do is to re-inject fresh water into the well, and then try to rebuild and the reservoir of fresh water here, and then try to flush back the salt. But in order to get really decontamination after a soil has been contaminated by salt, it's really a problem. So this is a matter of great concern, and it can be due to sea level rise, or it can be due to overdrawing of fresh water, because if you take from the wells the water, of course, you decrease the pressure of fresh water against salt water. And this is what is happening. So what has been done here is to build the Ridracoli Dam in order to increase the use of surface water resources for avoiding overexploitation of groundwater resources, because otherwise you get the wells contaminated. It's not really a matter of contaminating the soil, because usually, I mean, saltwater intrusion is a deep, it happens into the deep soil. But what may happen is that you get water for irrigation that becomes increasingly saline, salted, and then if you use this water for irrigation, you don't notice, of course, we can monitor the salinity. And if we try to use the water anyway, because you can't use it for civil use if you exceed a certain level of salinity, but you could use it for irrigation. But then you get accumulation of salt into the soil, which after a while prevents the use of, impacts the farming activities. So, I mean, it is indeed quite of a problem, and it is basically also explained but these figures are not so evident. But it is also explained here. You see, this is a natural environment where you have indeed some salt wedge intruding. But if you then draw wells here, and then you decrease the storage of fresh water, then you have salt water intruding more. And this is the problem, and also which is reported also in this figure here. And I think, okay. Okay, and now, predictions, as I said, are done with climate models, and I already discussed a little bit the problem of their uncertainty. What I just want to say here, very briefly, is that uncertainty is currently evaluated by ensemble simulation. So here you have prediction of temperature increase by different models. Ensemble simulation means that you use different models, and you use different initial and boundary conditions. And therefore, these different models allows you, with different boundary conditions, to obtain an envelope of possible future scenarios. And this is the way uncertainty is evaluated. In a nutshell, I want to say that this is an underestimation of the global uncertainty, And you can easily understand this, because imagine if all the models are wrong, you get an envelope, but this envelope doesn't contain the true value, the true future value, because all models are wrong. So of course there is another assumption here that the models, some of them are underestimating the change and some of them are overestimating. So it means that you assume that the true value is between the envelope of the models, but actually this is an assumption which cannot be proved. And also, if you look at the ability of this model to reproduce past data, you see that there is still a lot of discrepancy. So it's really an underestimation of uncertainty. And this is something that is not mentioned. And actually, for engineering, it is very relevant because, as you know, because we discussed this several times, for an engineer, getting a good estimate of uncertainty is compelling requirements. And we don't have to be, as engineers, we don't have to be concerned by a huge uncertainty. It's normal, but we have to find a flexible solution in order to compensate, to mitigate the effect of uncertainty. If we rely to underestimations, this is a problem. Here you see that this is, for a given emission scenario, is depicting a large variability up to 2100 from +2 to +2 with respect to a value of 0 that is fixed, I think, around 2000. There is written in the caption, actually, 2000. +2, +5, but still, this is an envelope that it's only part of uncertainty. I would call it model uncertainty, but it's ensemble uncertainty, but it's not corresponding to the global uncertainty of the prediction. And so just keep in mind that we have to be aware of this. Okay, and here there is a discussion on climate change mitigation and climate change adaptation, which I already mentioned, but here it goes in more details in order to discuss what are the measures that we can take in order to minimize the emissions and let's say minimize not only the emissions, the carbon concentration in the atmosphere. And we may reduce the emissions, but there are other methods called sometimes geoengineering methods, which consists of taking the CO2 from the atmosphere and storing it somewhere, like in geological formation or in depleted gas reservoirs, etc., or the deep ocean. But still, it's not clear whether these solutions are effective, because there is no assurance that once that you start, for instance, the CO2 in the deep ocean, you don't get an effect of the CO2 coming back into the atmosphere, released by the soil. So it's really something that is meant to accelerate the carbon cycle, because the carbon cycle actually is what brought to the formation of oil reservoirs and gas reservoirs, but it's not clear if this acceleration, human-induced acceleration, can in a way reproduce actually in the long term the carbon cycle and can lead to a real decrease of the CO2 in the atmosphere. So this is, and also you know that mitigation aims to reduce the emissions through the use of renewable energy, etc. Keep in mind that this solution has a social cost, which is a global cost, which is more relevant for, it's a global cost, but it's more relevant, more impacting on the poor zones of the globe, on the poor countries. And the social cost is significant.
But due to the higher cost of energy?
Yes, for instance, what you see today. What you see today, which is, okay, it's induced by the tension between Russia, not tension, the war between Russia and I would say the NATO. But Actually, I think that the problem is that we created in the past 20 years, a dependency, an energetic dependency of Europe from Russia. And actually now what at that time was deemed to be a smart policy, because it allowed us to reduce the emissions, because, you know, the natural gas is cleaner than fossil fuels. And now it turns out to be detrimental just for the perspective of mitigation of climate change, not to speak about political effects. And indeed, you know, it is a clear indication that you have sustainability as a social cost. And I think it is very relevant also to make, to plan the timing in order to make it sustainable. The policies to ensure sustainability, if they are not sustainable, this is a negative feedback, because you fall back, and falling back, it's a bit of a problem because you lose resources that you have invested on that. So what Draghi said, which I agree with, and let's turn on again our coal energy sources. Of course, we need to do that, but if we do that, this is indeed a fallback that it's a bit of a problem. And adaptation, and there are several proposed solutions. And here there is a list, and installing protective and resilience technologies and materials to protect from flood, changing vegetation, or changing agricultural practices. Irrigation, for instance, it's rainwater storage, serves also to save water for irrigation. And irrigation is, as you know, is using 70% of our fresh water consumption. And therefore, if we were able to improve the irrigation techniques in order to save water, this would be really a big step forward. And so there are several solutions that can be studied, which we don't discuss in detail because these are not really related to harbor engineering and coastal engineering. We already discussed about beach protection, coastal protections, and of course these can be also solutions to climate change adaptation. And so I don't want to go into the details here. And then keep in mind, and I want to conclude with this, I think it's the first, it's the last consideration. Climate models are not the only solution to design, to obtain future climate scenarios. I think that the way forward for the future is coupling climate models, prediction by climate models, with engineering techniques that focus on the technical requirement for designing climate change adaptation. I want to be more explicit. If I have to design a climate change adaptation measure to reduce the risk of coastal flooding, I need to have good prediction of waves, which means good predictions of extreme winds. And therefore, if the climate model is not able to give me the required resolution, the prediction that I need, then I think that we have to couple to the climate model a downscaling model, which merge the information given by the climate model in terms of predicted changes of relevant variables. So if the model is not, cannot predict the statistics of wind, to make an example, then let's use the climate model for predicting other statistics that are anyway relevant, like temperature change. Climate models are quite good in temperature, for temperature. So let's predict the temperature change. And then let's look at the historical data to seek a connection between temperature change and wind change or wave change. So by mixing the analysis of historical data, by mixing the analysis of the current situation with the prediction of the climate model, we have to find a way to get the most reliable predictions for what is the variable that is of interest for us. And this is suggesting a tight cooperation between climate scientists, hydrologists, and hydrologists or offshore engineers and structural engineers in order to find what is the best policy/solution for technical design in the presence of climate change. And this is what we are trying to promote. And a close connection which relies on using all the available information. And climate models are a very useful information, but for some variables they are very uncertain. And for prediction of ocean risks are for sure they are uncertain. And then let's use our information, our expertise to merge the information from climate models with the information from which is already available from historical data. Sometimes I see that there is the temptation of these two disciplines to move forward individually. So rely on the climate models or assume stationarity by engineers and in a way ignore climate change and focus only on climate variability, which I don't think it's a good way. Either way is limited because in the presence of this kind of challenge, we need to use all the information that we have available. I would say that this is the conclusion, and keep in mind that at the exam I don't make any question about climate change, but if you are interested, I think this lecture may give you much more information with respect to what I gave now to you, and by following the links. And in particular, if you are interested in raising sea level, the report that I have shown to you by Judith Curry, this is something that I found really interesting. Okay, I would say that this is that's it. And if you have any question, and then I would take some time to make a recap. Okay, so let's go back to our initial page. We started from here. Let's close here. First of all, I need to talk with Professor Archetti to fix the exam dates, but I think you may expect the first appeal around here. Let me just open a calendar. So let's go to May and June. I think the first exam date will be around 13, 14, 15, one of these 3 days. And it will be, I have to, what is your preference? Would you prefer to take the exam by both the modules, Professor Archetti and me, the same day, or would you prefer to, given that here you are just few?
I prefer, Professor, I prefer the both parts in the same day.
Okay. Okay, thank you. This is well taken. And what about you?
The Archetti exam is a presentation, credits, so yeah, I think we can do both on the same day.
Okay. So I will talk to her, and I think one of these 3 days will be the date. And then, as I mentioned to you, I think after 2 weeks we will fix another date, but and then another date in July. But it looks like you are few students only, so I think there might be the opportunity for some flexibility. It depends on the number of people. We need to start with the first date with the fixed date, because in principle there are more students that are subscribed to this exam. So the first date, I think we cannot say just contact us and see what happens. But if we see that the numbers are low, I think it's no problem if you want to if you wish further dates. I think we can agree by each other.
I don't know, we could, if you want a date, maybe Monday 13 would be good.
Yeah, I need to check with Professor Rocchetti. I said 3 days because I also have to check with my other exams. But I think that one of these 3 days is fine. This is the first issue. The second issue is our exam is, my exam is oral. Professor Rocchetti is, you are telling me that it's a presentation. And you know that in principle you are supposed to take the exam in physical presence. I say in principle because it's not clear to me, and then it's not clear to you as well, what is what will be the prescription by the university after May 31st. Up to May 31st, we were told that the students are supposed to attend the exam in presence, but exemptions are given to foreign students and students who may be in particular situations that cannot attend. And we need to see if this opportunity will be granted also after May 31st. I cannot say anything now. And I just would like to reassure you, I think that we will do any possible, we will adopt the max flexibility. And I don't think you have to be concerned by our exam in particular, because I think we may find a way. Indeed, I wouldn't want people traveling from abroad on purpose for this exam. But of course, you have to make an overall assessment of the situation. And because maybe that several other my colleagues require the physical presence, because actually what the university requires, we should take it. And so maybe that indeed you have to plan a physical attendance anyway, but I can't really say anything about this. But in any case, the essence of the exam doesn't change, even if it's in person or remote. It's an oral for me. I think we can manage to make the exam in Ravenna, or otherwise in Bologna if it's more convenient for you, but I don't have any problem to travel here. And so my exam, as I mentioned to you, is oral. At the beginning, I also explained how it takes place, the duration, and it is expected to last for 20 minutes, half an hour, no more. Usually 3 questions. I value your presenting abilities. For the 2 of you attending in physical presence, I already had the opportunity to make a check, and the check was fine. I mean, the presentations were okay, which means that your oral exam probably will last less than 20 minutes, because I consider that the first question in a way has been already or dealt with. What are the questions that I may ask? So usually, as I said, the first question is more descriptive, and then some specific ones. So I would like to go through our lectures in order to make a recap. I start, you know, the first lectures are not really, I don't think here there are many questions to be mentioned. Just keep in mind that my questions could be also very trivial, like how would you define a coastline, or what is a groin, what is a breakwater, what is the purpose of groin and breakwater, what is the difference between the 2 interventions. So why people build groins, why they build breakwaters, and what could be the negative effects given by breakwater and groins. So these are trivial questions on the one hand, but on the other hand, they allow me to see, to check whether you really try to elaborate an overall perspective of what we discussed. If you have the clear idea of what is the problem, what are the solutions, these are important things. And keep in mind that I may also ask something that is not directly related to what I explained, but I know that Professor Archetti taught to you, like what is wave height, what is wave amplitude, what is the relation between the two, wave frequency, wave period, trivial questions, but sometimes I use them in order, as I said, to check whether you have clear the topic and the situation. But I would say that for this first lecture, I mean, besides saying that be careful of the definitions, of the basic definitions, be careful of the orders of magnitude. So, what can be an extreme wave height? Half a meter, 100 meters, 1 kilometer. I mean, these are trivial questions, but the general suggestion is try to figure out an engineering perspective of the problem and the solutions. Now, and then there is port planning and environmental impact. So I could ask something about the loads, like this would be an ideal first question, which is not specific, like what are the loads? Can we speak about loads on a berth? So from the seaside, from the berth, from the land side, and a discussion of this figure. But as I said, this is an ideal first question. There is a lot to say, but as a general indication, when there is a lot to say, you may feel like the answer is easier because you can, I mean, you don't run the risk of having nothing to say. But on the other hand, when you have a lot of things to say, it's important that you make a synthesis, that you go straight to the essence. If you are supposed to speak 5 minutes, because what I said, if you remember, is the first question may take 5-10 minutes, and the other questions are more like a couple of minutes, more succinct, more synthetic. If you have to speak 5 minutes, try in 5 minutes to go straight to the essence, and you shouldn't forget anything relevant, but at the same time, you should be able to make a synthesis. And a general suggestion that doesn't apply to me only, when you are asked a question, reply to that question. It may seem trivial, but it happens very frequently, especially when there is the opportunity to adopt some flexibility, that the students don't reply to the questions that have been asked or only provide a partial reply. So try to be very focused, and when there is a lot to be said, just try to be very effective in what you have to say by taking into account that you are an engineer. Okay, and then design life, this is maybe a question, like what is the design life of a breakwater, of a berth structure, of rubber fenders. Of course, if you, instead of saying 100 for breakwater, you say 50, it's not a problem. The important thing is that you are aware of the difference between fenders, 10 years. Why? Rubber. It's clear that they cannot last for 100 years. And breakwater, 100 years. Why? Because you cannot substitute a breakwater every 5 years. So, I mean, the design life, and just, it's important the order of magnitude. Okay, and another typical first question is, what are the most typical berth structures? Solid structure, open structure, etc. And I think it's unlikely that I ask something related to these rules of thumb. I'm talking specifically about these. Okay, and that's it. Let's go forward. Forcing estimation. Beware of these definitions, length overall, drought, or draft. This is something that I may ask. What is length overall? And I may ask, just draw a sketch of a ship and show me what is length overall, or and then wind forces. The windrows may be the subject of some questions, very specific one. What is the windrows, and what is the information that I can get? How do you estimate it? Another possibility, probability. Sometimes I ask, what is probability? This may be a second or third question. What is probability? And because I think that you have to be able to define what is. And you may reply with the definition, a frequentist definition, like probability is equivalent to the frequency of an event, to the expected frequency. And you may also mention Kolmogorov axioms, which are linked somewhere here. Let me see, Kolmogorov. It is an alternative way here of defining probability. You may also reply with Kolmogorov axioms. Even if, for an engineer, I would expect that you say something about the analogy between frequency and probability. If you also mention the Kolmogorov axioms, it gives value to your answer. Okay? And this is a possible question, yes. I don't ask anything related to probability distributions, I mean, and for sure not you shouldn't learn by memory any relationship for the probability distribution unless Professor Archetti asks you the Gambit distribution. I don't know, but I'm not asking it. And wind forces, if you could please remember this relationship here. Okay, and specify what is. I don't think you need to, this one, absolutely not. And wind loads, I don't suggest to learn anything related to wind loads by, let me see, no, sorry, I was wrong. Wind loads, I would say, let me see. I don't think there is anything that you have to learn about this. Also, these definitions of the Brest lines, it's not really needed. Vessel rotation, if you could just explain what is a rotational moment, when it's originated the rotational moment. And wave forces, forget about it. Concentrate on wind, and I mean concentrate in terms of learning by memory. Forget about waves and currents. It's not needed. I don't think the design wave is not something that is relevant to me. And here, of course, try to remember these terms, even if it's not really, I mean, try to be very, very efficient in selecting those terms that help you to you see that may help you to get a perspective of the problem, and may help you when you have to speak about some colleague to explain what you have studied. So it's try to get the language that you feel it's more effective, more needed, I would say. And this is a suggestion. So I wouldn't say that you have to learn everything of yaw, pitch, roll, heave. It's not really needed, but try in a way to get an efficient also panorama of the terms. Okay, nautical terms, there are a lot of them. Try to make your own selection of what are more useful to you. And then I think that if you reason in these terms, if you get a reasoning in this term, it's effective, it's fine. Okay, and let's forget about this relationship. Now, another thing is beach protection strategies and structures, I don't think there is much to say here, besides saying you have to know what is a groin, what is a breakwater, what is a seawall, and what is their purpose. Beach design of groins, yeah, the lambda 1/3 rule. Okay, this is the essence that you have to learn. The lambda rule, yeah. And also the rules of thumb. What is the minimum spacing, 20 meters. There are some rules of thumb here. It would be useful if you could learn these steps. I mean, it's not a problem if you miss one of them, but I mean, the most important ones, just to try to, and also just these typical dimensions. This is something I may ask. What is the typical dimension of a groin? Beach hydrodynamics and morphodynamics, you have to learn the proof of this, of the CERC formula. That's it, this integral. Okay, and then it's fine, because what follows, I think it's not a big problem once that you remember the concept, which is energy means sediment transport after the breaker line, and then there is this integration in order to compute the energy, which is what you really need to know. And then stability, yes, the sheet criteria, that's it, okay? And you don't need to remember with me the Hudson formula, but the sheet criteria, yes, please. And also, you don't need to remember any formula for computing hiding, for computing what happens with the slope, the surface, the action of waves and currents. This is not necessary. But the sheets criteria, if you could remember how to this equilibrium, how we can derive it. Design of breakwater, there is nothing, because what I gave here, what I taught more than Professor Archetti, I think it's related to run-up, wave transmission, and setup. But let's just remember what is wave setup, what is wave transmission, and what is wave run-up. And I think that probably it's enough. Dredging, I mean, there is nothing really that I usually ask about dredging, and nothing about climate change. That's it. I would say that this is the panorama that I can give. Okay, I am a little bit early, but I think we can pass to your questions if you have any, but I just confirm that I am available for any question from now to June, whenever you want. And it's better if you contact me by email rather than Teams, because email is safer. Okay, Teams is a little bit more. I use it during the lecture time, but after the lectures, maybe that I don't check it every day. Do you have any specific question now?
No.
Okay, very good. Okay, I would like to thank you, because I appreciated your willingness to come in presence, or for you, Kashayar, to attend remotely and with perseverance. So thank you very much.
Thank you, Professor. Thank you to you.
Yeah, and I hope to have the opportunity to see you in presence one day. Otherwise, we will see virtually at the exam each other.
I hope so too. Have a nice day, Professor. Thank you.
Yeah, you too. Bye-bye.